So we'll just wait for a couple of minutes and then we can start. I think we can start. So today we are just a second. So today we'll be discussing problems related to week 9 material. And if you have any doubts and questions regarding a particular problem, I'll just give you time after that problem and you can ask your doubts. And other than that, I don't think I will have to give out any guidelines. So let me just start. So good afternoon, everyone. My name is Musab Rafiq. I'm your course TA for the course Digital Circuits that is taught by Professor Shantanu Chattopadhyay from IIT Kharagpur. Today is the live session. Today it's the ninth live session of this course, where we are going to discuss problems related to week 9 related material. I'm a PhD student at Department of Electrical Engineering at IIT Kanpur, and other than me, there are two other course TAs for this course. So today we are going to discuss problems related to memories, the organization of memories, and also problems related to Hamming codes, error finding in Hamming codes. And other than that, I think this much we are going to discuss in today's live session. And let me just start with the first problem of today's live session. This is a simple problem. It states that each cell of a static SRAM cell contains A 6 MOS transistors, B 4 MOS transistors and 2 capacitors, C 4 MOS transistors and 2 MOS transistors. So you people are aware of this thing that each SRAM cell contains 6 MOS transistors. That is option A. So each SRAM cell has a 6 transistors. So let me just admit the student first. So now let's discuss briefly about this SRAM cell. So here we have the circuit for this 60 SRAM cell. We discussed in previous question, that was the question number 1 of today's live session, which asked us how many MOS transistors are there in this SRAM cell. Typically in a 60 SRAM cell there are 6 transistors. 60 here refers 6 transistors, 6 MOS transistors, right? So this whole thing is your 60 SRAM cell. So in 60 SRAM cell, the cross coupled inverter is the core of this cell. So when I say this cross coupled, this thing, the cross coupled inverter pair, it forms the core of the 60 SRAM cell. And the data is stored on these nodes as in the form of charge as Q and Q complement. Due to the symmetric nature of this thing, the architecture, this data is stored in complementary fashion, like so this Q and Q bar. If it is storing 0, here it will be 1. If it's storing 1, here it will be 0. And these storage nodes, that Q and Q bar, they are connected to the bit lines here, bit lines BL bar and BL via access transistors. So what I have said so far is this cross-coupled inverter pair forms the base of this 60 SRAM cell, and this thing, this is your CMOS inverter. Here you take the output and here it's your input. This is your supply VDD, and this is ground. So this is your CMOS inverter, and here you have two inverters, M1, M2 forming one inverter, and M3 and M4 forming another inverter. And these are your storage nodes, and these are connected to the bit lines via the excess transistors or pass transistors M5 and M6. These are NMOS transistors, right? So you can also draw this thing as like, if you want a bit simplified schematic, you can draw it like this. So this thing represents one inverter, this represents another inverter, and together with, so this will be your word line, and this here is your bit line, and this is your bit line bar. So together you can also write like this. So these are the points I discussed here. So you cross-coupled inverters form the core of 60 SRAM cell. Due to the symmetric nature, data stored on Q and Q complement is always complementary. Storage nodes are connected to the bit lines via access or pass transistors that are M5 and M6. So now going forward, there are, let me just admit a student first, sorry about that. So going forward, there are three operations related to SRAM cell. They are hold, number one, number two, read, and number three, write. So when you talk about this hold operation, it means that the word line is grounded. Word line is grounded. So what I mean to say, first of all, in hold, no read, no write is performed, right? And also word line is grounded. So this is simply your hold operation. So what is the hold operation? No read and write is performed, and word line is just simply grounded. After that, we have a read operation. So let me just explain one read operation here. Let's just assume Q equal to 1 is stored here and Q bar equal to 0 as the this is symmetry complementary, so Q bar equal to 0 will be stored. Now we want to read this data. So how we read it? What we'll do? We'll precharge bit line and bit line bar to VDD. So bitline and bitline complement are charged to VDD. After that, what is done? Word line is asserted high. So by word line asserting high, I mean to say word line is given as VDD. So once word line is given as VDD, this VDD is at this at M5 and the M6. Now you see here it's charged to VDD, and this is also charged pre-charged to VDD. Here you have Q bar equal to 0. That means at this left hand side there will be a discharging current flowing from M5 to M1, and as a result this thing will get discharged to ground. So there will be a discharge of ground because of this Q bar equal to 0, and this thing will remain at VDD. So once this was VDD with line complement, and now it goes to ground, that means Q bar is equal to 0 and Q equal to 1. So in this way we can just read the state. This was related to the read operation of the 60 SRAM cell. Now towards the read operation of the 60 SRAM cell, let's just consider initially Q equal to 1 and Q bar equal to 0 are your states. So Q equal to 1 and Q bar equal to 1 are your initial states. Q bar equal to 0 equal. Now you want to write the Q equal to 0. Basically you want to flip the states. Now I want to write Q equal to 0 and Q bar equal to 1 automatically. So what I will do, it is done in two phases. In phase 1, whatever value you want to put, we'll put that on the its corresponding bit lines. So we want Q equal to 0. So bit line will be precharged to ground, means bit line will be connected to ground, and bit line bar will be precharged to VDD, right? So it will be here grounded, and this thing will be charge VDD. Now also what will happening once and then this was a precondition. Now two phases will occur. Now word line will be asserted high. Word line will be asserted high. Now initially Q equal to 1 and BL equal to 0. So what will happen? Once word line is asserted high, a discharging current will flow from M4 to M6 and this Q will tend to 0. This thing now is grounded. This is was 1 and discharging current will flow through this and this Q will tend to 0. In the second phase, as this Q will tend to 0 because of this symmetric nature, as an input to this inverter M2 M1, Q bar, as Q is tending to 0, Q bar will tend to 1. So you know this from the VTC characteristics of the inverter, as this is your V out, this is your V in. As V in is increasing, V out decreases. As V in is decreasing, V out increases. So as Q tends to 0, Q bar will tend to 1. In this way, we write the contents of the SRAM cell. This was just a basic info regarding the 60 SRAM cell, the hold operation, the read operation, the write operation. There are many things to discuss here. Like we have this pull ratio, cell ratio, where we need proper sizing of these transistors M1, M5, M4, M6, and we need to like cell ratio that strength of M1 needs to be greater than the strength of M5 and the strength of M6 need to be greater than the strength of M4 and the proper balance needs to be struck. That thing I feel like it's quite not at the level of the bachelor's. Maybe in some higher semesters, you can always refer to those concepts, and even in masters, definitely you will just check them out. But if you feel like you need to get a bit more about this, you can always refer this book from John M. Rabai, this Digital Circuits, where you can get the complete idea of the workings of 60 SRAM cell. And if you want to dive more into this 60 SRAM cell, you can also refer this latest book by Professor Shimangyu from Georgia Tech, the semiconductor memories. You can always refer to these books. But at a bachelor level, I feel like this much is, in fact, this is a basic course, digital circuits. I think usually polytechnic students and third sem students deal with it, and I feel like for them, this is this much knowledge is quite more than enough. So this was just the working of this 60 SRAM cell, where we first discussed this hold operation. First the structure of 60 SRAM cell, then we discussed this hold operation, then we had a look at the read operation, and finally we had the look at the write operation. How we approach this question, because first we had this problem which stated that how many transistors are present in what is 60 SRAM cell, or this SRAM cell made up of. And also I like to mention this 60 SRAM cell, other than 60 SRAM cell there are other SRAM architectures as well. We have this 80 SRAM cell where we have 8 transistors and we have a read word line separate and write word line separate. So there is a decoupling of this read part and write part. So there are other architectures as well. So, is there any doubt? Are there any doubts in this? What should I say in this portion? If not, we can move forward to question number two. Is this clear? I assume there are no doubts. If you have any, please let me know at the end or anytime you like. So now we have question number two of today's live session. So it states that which of the following statement is true? This is a simple true and false type question. So number one option is accessing any memory location in a RAM takes same amount of time. Accessing any memory location of sequential SS memory takes same amount of time. Low cost memory can be designed using SRAM cells. SRAM cell memories need a periodic refreshing circuit. So among the four options, only one option is correct, and that is option A. That is accessing any location in a RAM takes same amount of time. And when we talk about these SRAM cells, they are costly. Their speed of operation is quite high, and they don't need any refreshing circuit. They are a volatile memory. So SRAM cells are costly. So only option A among the four options was correct. Now towards question number 3, a programmable logic array can be used as a microprocessor to as a dynamic memory to realize a sequential logic. Option D, to realize a combination logic. So a PLA can be used to realize a combination logic. You people are aware of that, and in fact, one of the questions will deal with that at the end. So a PLA is simply used as can be used as a combination to realize a combination logic. Now, here is this question. I would like you guys to tell me the answer first. Then I will just discuss about this DRAM cell. So the minimum number of transistors required to make a dynamic RAM cell is anyone? How many transistors minimum number is required to make a DRAM cell? Yeah, one of the student has written the answer. So you are right. So minimum there are one transistor required. Other than that, do you know any other configuration? How many transistors will be required for that? This is one configuration where minimum number of transistors is one. Other than that, do you know any other configuration? How many transistors are required in that configuration? One is correct. Your answer one is correct. Other than that, you know any other configuration? Yeah, let me just show you. So first we'll answer this thing. So this is your dynamic RAM cell. It will require one transistors, and we refer to this type of DRAM cell as 1T1C. One transistor, one capacitor. This is your 1T1C. What should I say? DRAM cell. Now let's just take a look at the DRAM cells. There are basically two type of DRAM architectures, popular ones. There are also nowadays people are targeting capacitorless DRAMs as well. But let's not discuss that thing. That will be that much is deviation from our main topic. So let's just not digress in that direction. Let's just have focus on this only. So this is 3T DRAM cell, also called as 3T1C structure. So this is your 3T1C structure, and there are two operations involved: read and write. So first of all, let's just take a look at the architecture. It consists of three NMOS transistors, M1, M2, and M3. You have two bit lines, bit line 1 and bit line 2, and you have two word line that is write word line and read word line. So write word line is here and read word line is here. Now let's just discuss the write operation. So whatever value you want to store, we'll just put it on bit line 1. So we will just precharge bit line 1 to either 0 or VDD based on our logic we want to store. Now, as we put the value on bit line 1, we will assert the word line high, write word line high, that is WWL. Now, as we assert this write word line high, this M1 transistor will turn on, and if it was 1, this 1, because of this charge sharing, will be get stored on this X. And if it was 0, this thing will be discharged and it will remain at 0 only. So 1 or 0 will be stored on this capacitor, right? As we assert word line high, 1 or 0 will be stored on this capacitor at node X. Now after that, we need to read the state. So how will we read the state? We will precharge the bit line 2, that is BL2. We will precharge bit line 2 to VDD. So we will precharge this thing to VDD, and we will assert the read word line high. So this thing. So asserting read word line. As we assert the read word line, so based on the value stored at X, this M2 will be on or off. So if 1 was stored at X, M2 will be on. If 0 was stored at X, M2 will be off. If 1 was stored, M2 will be on. If 0 was stored, M2 will be off. So if 1 was stored, So both these transistors are on, and as a result, discharging current will flow through this thing, and VDD will tend to ground. If 0 was stored, this thing will remain off, and the bit line 2 will remain at bit line 2 VDD. So you see this, when 0 was stored, my bit line 2 is at VDD. When 1 was stored, my bit line 2 gets discharged to 0. So whatever logic was stored, its opposite is happening at bit line 2. So this is a inverting kind of a readout. So if 1 was stored, my bit line precharged bit line 2 is discharging to 0, and if 0 was stored, my bit line 2 will remain at high, that is, it will remain at charge to VDD. So it is an inverting kind of a readout. And here, to accelerate the speed of operation, we use sensamp. So sensamp, basically it kind of detects the discharge of this bit line, and it accelerates the discharge, and we get a faster readout. So it's not a necessity, but it is used to increase the speed of operation. So this was working of a 3T1C DRAM cell. We also have one more architecture, which is 1T1C, that you guys are, I think, familiar with. So this is your 1T1C architecture, which is also sometimes referred to as 1T DRAM, right? So here we have a, word line that is shared between the read and write path, and we have a single bit line. So whatever value, so first we'll discuss write operation. So whatever value we want to store, we'll put it on bit line on this capacitor CBL. So CBL will be either grounded, or that is 0, or it will be precharged to VDD by 2. Here it is precharged to VDD by 2. No, sorry, I'm just discussing read operation. Let's just discuss the write first. So it precharged to 0 or VDD, right? Then word line is asserted high. So based on the value on CS, a charge distribution will take place, and CS will get either precharged to VDD, or it will just be discharged. Now for read, we will put CBL, will precharge CBL to VDD by 2. We'll precharge CL to VDD by 2, and we will assert the word line high. Once we assert the word line high, charge distribution will take place. Either this will go up if this was 1, or this will go down if this was 0. So what will happen if this was VDD by 2, the charge on bit line, during the read operation it will slightly increase, and this will slightly decrease. For this is for the case 0 was stored, this is for the case 1 was stored. But to drive these two values to VDD and ground, sense amp is used here. So sense amp is a necessity in 1T1C structure. In SRAM and 3T1C, it was just to increase the speed, but here it is necessary, because typically this when we precharge to VDD by 2, to the change, that is del V, is typically around 100 millivolts. So this is not this 100 millivolt is not sufficient to drive it towards the VDD or towards ground. So sense amp is used here. So these are some of the basics for this 1T1C, 3T1C DRAM cells, and also we discussed something about SRAM cell in the start. So any doubts, any queries regarding this much? So also, if you want to have a thorough look at this, you can refer the book Jan Amrabai, The Digital Integrated Circuits by Jan Amrabai from this UCB, University of California, Berkeley, and also you can refer to Semiconductor Memories from Professor Shimangyu. So have you seen this type of architecture, this 3T DRAM, anyone before? Okay, okay. Was the working clear for 3T? Okay, that's fine. Actually, this was not in your syllabus, so I thought I'll just give a brief overview of this. Anyways, you can refer to your books that I mentioned. Other than that, I think this much is sufficient for you guys. So now let's just discuss the problems of today's live session. So now we have problem number 5. Just a second, let me just water first. So, question 5 asks us find the 12-bit Hamming code for the given 8-bit data word. So, we are given with this 8-bit data word and we need to find out the 12-bit Hamming code. So, basically, we need to find out the parity bits. So, how I approach it, let me just draw a table. I don't want to mess it up. So, table, so how many? 1, 2, 3. 1, 2, 3. So, let me just So these are my bit numbers 2, 3, 4, 7, 8, 9, 10, 11, and 12. This is your parity bit P1. This is your P2. This is your data bit D1. This is your P4. This is data bit D2. This is data bit D3. This is data bit D4. This is P8. This is D5. This is D6. This is D7, and this is D8. Right? Now here we don't know these values. Let me just write the data first. That is 1 0 1 0. I'm just writing the data bits and 1 1 0 0. Now we need to figure out these P1 P2 P4 and P8. So for P1 P4 P8, how will we do it, how we can find those values? So P1 will be XOR of, just a second, mouse is correcting. So P1 will be basically XOR of 3, 5, 7, 9, and 11. So XOR of all those data bit terms which have 1 in them. So by 1 in them, I mean to say when you have this 8421 structure, so let's just say we have 3. So 3 is basically 2 plus 1. So 2 plus 1. So 1 is here. You have 5, 4 plus 1. So 1 is here. So that's why I'm saying data bit T 3, 3. 3, 5, 7, 9, 11. So 3, 5, 7, 9, and 11. So XOR of 3, 5, 7, 9, 11, that is XOR of 1, 0, 0, 1, 0, and that is 0. So P1 is 0. Next we have P2. XOR of all the bits where we 2. So that is 3, 3, 6, 7, 10, and 11. So this is XOR 3 it's 1, 6 it's 1, 7 it's 0, 10 it's 1, and 11 it's also 0. So this thing will be equal to 1. So P2 is 1. Now P3, P4, I call it P4. P4 is XOR of 5, 6, 7, 12. So P4 is XOR of 5, 6, 7, 12. and that is XOR of 5 is 0, 6 is 1, 7 is 0, and 12 is 0. So that is 1. So P4 is 1. Now P8 is XOR of 9, 10, 11, 12. That is XOR of 1, 1, 0, 0. And that thing is 0. So my P8 is 0. So ultimately my whole code will be P1 is 0, P2 is 1, P4 is 1, and P8 is 0. So my answer will be then equal to answer will be then equal to 0, 1, 1, 0, 1, 0, 0, 1, 1, 0, 0. So it is 0, 1, 1, 1, 0, 1, 0, 0, 1, 1, 0, 0. That is option B. So option B is your right answer. So option B is the 12-bit Hamming code for the 8-bit data world. So is this clear? So 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 I assumed you would have taken a look at lecture. So I also mentioned it. So basically parity bits are at P8, right? P4, P2, and P1. So we have 1. So how you represent 1? I'll just call it as in 8421 representation. How you represent 1 is 0, 0, 0, 1, right? How you represent 3? You write 0, 0, 1, 1. How you represent, let's say 5? So 4 plus 1, 1, 0, 1. So now check 1, P1, wherever is P1, it's in 1. So leave 1 because 1 we are just finding out. So it's at 3, right? 3, it's at 5. It will be at 7. So 7 will be somewhat like this. Now wherever it's 2, we'll just write P2. So P2 will be present in, let's say we have number 3. So 3 will be represented in 8421 like 0, 0, 1, 1. So this is your 2, right? Now we have 5, or should I say 5 is 4 plus 1, 6. 6 is 4 plus 2, so 6 can be written like this 0, 1, 1, 0. So we have bit 2 here also. Then for P8, let's just take a look at 10, decimal 10. So 10 can be written as 8 plus 2, 1, 0, 1, 0. So you have 8 also, you have 2 also. That's why P8 will have 10 and also P2 will have 10. Right? You got an idea what I'm saying? So, no, tell me, you got it? No, I can just repeat it. It's not a big deal. It's a pretty simple task. So, just a second. Yes, so all our places where 1 is 1, I'm to say at once that P1 position, that is what should I call the first bit position, there is 1 in 8421 representation. I'll just mark all those bits, I'll just use all those bits for finding P1. So you check it, these are all odd numbers 3, 5, 7, 9, 11 because all of them will have 1. And then we have 3, 6, 7, 10, 11. So in decimal 6 we have 4 plus 2. So 4 will also be there, 2 will also be there. So while finding P4, 6 is I am also taking 6. While finding P2, I am also taking this 6 bit. Right? This is for finding the Hamming code when we are using this even parity. Yes. Okay. So now I have this question. I would like you guys to do this first, then I'll just show the solution. So this question reads as a 12-bit Hamming code is read from a memory location. This Hamming code contains 8-bit data and 4-bit code word. So what was the original 8-bit data word stored in the memory location if the 12-bit Hamming code is 1101 0100 1010? So the received Hamming code is given. You need to find out the data word. So I'll just give you 5 minutes. You guys can do it. Then I'll just show the solution. So has anyone done it? Yes, option A is correct. So let me just show the solution. So So our 12-bit code that we received was 1 1 0 1 0 0 1 0 1 0, right? So 1101 0100 1010. Now we need to figure out whether this receipt code has any error bit, and then we'll find the position of that error bit if there is, and then we'll just correct that bit and we'll just say what is the original data word. So this is the code that we received. Now we'll just find the check bits. We'll do the check bits. So now we'll do XOR operation between 1 3 5 7 9 11. So here you see I included this one because now I'm checking, so this parity bit will also be included. So this is the XOR operation between 1 0 0 0 1 1. So this thing will be equal to 1. Then I have C2, so this is XOR between 2 5 6 2 5 6 7 10 and 11. So this is XOR. So this is XOR 1. So 3 is also 3. 4 plus 1 3. So this is 3. 1 0 1 0 0 1. So this thing is also equal to 1. Then C4 is XOR between 4 5 6 7 4 5 6 7. Then it's 9, it's not there, 10, yeah, 12, yeah, right. So it will be XOR of 4 will be 1 5 0 6 1 7 0 and 12 0. So it will be 0. Then I am having C8, so it will be XOR of 8 9 10 11 and 12. So it will be XOR of 0 1 0 1 0. So this thing is 0. So there is error, and the error is at the bit position that will find out like this: C8 C4 C2 C1. So it's C8 is 0, C4 is 0, C2 is 1, and C2 1 is 1. So that is 2 plus 1, that is third bit. Third bit is having error, so this thing. So if it was 0, it should be 1. So my data bits that are these things: 1 0 1 0 and 1 0 1 0 coming from these 3 bits. So this is my correct code. So this is my original data word: 1010 1010. So that is option A, which is the correct answer. So someone has written P1 is error. P1. What P1 is error? Maybe. Okay, so option A is the correct answer. Now towards the next question. Yes, yes, D1, yeah, D1, correct. D1 is there is error. So third bit means D1. I hope you got it. So basically output data word, right? I have to write data word. I know data word it has positions 8, 9, 10, 11, 12. Sorry, 9, 10, 11, 12. So this one. And at positions 3, 5, 6, 7. Positions 1, 2, 4, 8 are reserved for parity bits. So after the whole process, I found out that the error was at bit position 3. So 3 means data 1. So my if there was no error in the received code, my data word would have been 00101010. But I found out that there was an error at D1. So I found out this 0 is not correct, so it should be 1. So I wrote 10101010. So this was my original word, data word. So these are my data bits, right? D1, D2, D3, D4, D5, D6, D7, D8. And these are my parity bits, this one. I found out the error is at 3. I corrected that and I wrote the original data word. It's clear. So now let's move forward to question number 7 of today's live session. It states that in Hamming code, how many check bits are required for a data word of 25 bits? So we are given that the data word is having 25 bits. So we represent this thing by n. And we need to find out how many check bits are required. So check bits are written by k. So we have this condition for the Hamming code that needs to be followed. That is 2 raised power k should always be greater or equal to n plus k plus 1. So you need to keep this condition in mind. So here n is equal to 25, k we need to find out. So we have a condition 2 raised power k should be greater or equal to n is 25 plus k plus 1. That implies 2 raised to power k should be greater or equal to 26 plus k. Now for n equal to 4, so this is 2 raised power 16, so that's obviously less than 26. So n equal to 5, let's just put n equal to 5. We have 2 raised power 5 should be greater or equal to 26 plus 5. That implies 32 greater or equal to 31. So this condition is satisfied. So that implies n is equal to, sorry, k is equal to 5. K is equal to 5. So number of check bits required for a 25-bit data word is 5. Now another question along these lines I would like you guys to do first. So it asks us what is the size of the Hamming code for a 32-bit data word. So you need to find out the size of the Hamming code for a 32-bit data word. So has anyone else done it apart from the one of the participants? Has anyone else done it? Among the other participants, have you done it? If you have done it, please write yeah. So any other? So let me just show the solution first. So we again have this condition for a Hamming code 2 raised power k should be greater or equal to n plus k plus 1. So here n is equal to 32 and k we need to find out. So 2 raised to power k should be greater or equal to 32 plus k plus 1. That implies 2 raised to power k should be greater or equal to 33 plus k. So again, let us say k is equal to 5. So 32 greater or equal to 33 plus 5. So that is 38. 32 is greater or equal to 38. So this is incorrect. Now k is equal to 6. So 2 raised power 6 is 64. 64 is greater or equal to 32. 3 plus 6. So 64 is greater or equal to 39. So n is equal to 32. K is equal to 6. So total word length of Hamming code is 38. That is option B. So option B is the correct answer. Now I have another question. This is a simple question. So I'd like you guys to tell me the answer. So which type of memory has a constraint of minimum operating clock frequency? So electrically erasable PROM, static RAM, dynamic RAM, or magnetoresistive RAM. We also call it as MRAM. So among the following, which has the constraint of minimum operating clock frequency? Anyone? So question number 9. I would like to repeat the question. Which of the memory has a constraint of minimum operating clock frequency? So one thing I forgot to mention when I was discussing DRAM, do you know why it's called DRAM? This dynamic random access memory. Anyone? Why this word dynamic? Can anyone tell me why this word dynamic comes in there? Yes, correct. So this refresh is basically your dynamic thing that is in DRAM, and this refresh operation basically means how you do this refresh operation. Basically, refresh means read plus write. You read the state, you write the state. Read, write. So that is driven by your clock. So this dynamic thing, this usually that is stored on the charge on the capacitors. These capacitors tend to charges tend to discharge from these leakages happen on these capacitors, and you need to read the state after some time. Typically, by industry standard, a DRAM has having a refresh time of 60 milliseconds. That is the industry standard. It should have a refresh time of 15 milliseconds at least. For 60 milliseconds, it should be able to retain its state. So within those 60 milliseconds, you read the state, you write the state again. So you are just reading, writing, reading, writing. So there is a constraint based on the clock. So your clock is refreshing on this is driven by the clock. So the dynamic RAM has a constraint of minimum operating clock frequency. And to your operation, this MRAM is a non-volatile memory. It doesn't have anything to do with this clock thing. And SRAM is your volatile memory, and EEPROM is your read-only memory. So the constraint of a minimum operating clock frequency is on DRAM because of its refresh rate and all. So Option 3 is your correct answer. Then, which memory is difficult to interface with the processor? A. Static memory, B. Dynamic memory, 3. ROM, and 4. None of these. So, among these options, again, dynamic memory, it's quite difficult to interface with the processor. Static memories are, if you look at the this table, memory hierarchy, these cache memories, L1, L2, L3 cache, they are quite interfaced with the processor. These L1, L2, L3, they are simply made up of these your SRAM cells, and then they have this dynamic memory, which you in main memory, which we call or in layman terms we call it RAM. That you often say that how much is the RAM of your PC, how much is the RAM of your phone, that is your DRAM. And when you talk about the caches, cache memory, that are quite close to the interface, that are close to the processor, that are your static memory. And when you look at this memory hierarchy, the as you go down, the cost of the memory decreases, but the speed of the memory increases. I mean to say the cost of the memory decreases, but the speed of operation also decreases. That means static memory is very fast as compared to dynamic memory. So this is your what should I say? Dynamic memory is difficult to interface. Let me just show this if I can that figure. Just a second. Just a second. I think I have that figure with me. So this thing I was just referring. So as you go down this memory hierarchy, capacity and access time are increasing, but and also as you go down, this cost is also decreasing. I was saying this thing. So someone has raised the hand. So interface, you mean to say on the same at the same place you want to have this. So if you see this processor and memory, they are separate units in that. So it means to say they are because I don't know the exact reason or difficult to what's the difficulty here, but when you talk about these registers, they are present in your processor. There are also at the processor and your cache, that is level 1, level 2, and level 3 cache. They are near to the processor, so there is they are quite interfaced with the processor. But these dynamic RAMs, they are a separate entity that are in your memory unit, right? So, but the difficult, yeah. Yeah, it's slow. Their speed of operation is because you see the when if you talk about this von Neumann bottleneck, have you heard of that? Yeah, yeah, architecture. So you see that speed of operation quite increased in processors, but the memory this yeah, and you need to fetch all the time. You need to fetch from main memory. So that's the reason they are not because we also call it as a memory wall. If you have heard that of that term, memory wall. You refer if you can in detail if you want to check it, you just say this memory wall, because if you see over the years this speed of operation have quite increased tremendously, your clock frequencies have increased, but to interface them with at the same clock, I think that's a difficult operation, and every time you need to fetch this contents from the memory, so it becomes difficult, and that's why the fast memories are put closer to the this thing yeah. You can all, if there is anything else, I'll just update you. Right now, I'm getting this reason in my mind. Yeah. So now let's just have another question. So we need to find out the Hamming distance between the codes 1101011 and 1000111. So we need to find out the Hamming distance. So we have code 1, that is 11001011, and we have code 2, 100000 and 111. So Hamming distance is basically C1 XOR with C2, and then we count the number of ones in C1 XOR C2. So we have 11001011, and other we have 100000. So how many zeros I written? One, two, three, four. I had to write only one, one, one. Now we'll do the XOR operation. So it's 0, 0, 1, 1, 0, 0, 1, 0. So number of ones are 3. So how many distance is 3? Is this clear? Basically, at 3-bit positions, they are having different values. Just simply. So now let's move forward to question number 12. So I would like you guys to do first. It's based on the previous questions that we did. It says that the final code after encoding data bits 1101 into 7-bit even parity code Hamming code is. So you need to find out the 7-bit even parity Hamming code for data word 1101. My cursor got missing somewhere. Let's try. Okay, found it. So anyone else? Only one participant has so far done it. I expected all others to do it. So are you facing any difficulties in solving this to the other participants? I'm saying, or you guys are still doing? Okay, so let me just show. Actually, this was bit easy as compared to the other questions we had. So what is given is the data bits 1101. So we need to find the parity bits. Three parity bits will be required. So we have P1, P2, D1, P1, P2. So 1, 2, 3, P4, P, D, D2, D3, and D4. So these are your 5, 6, 7, right? So we know this much 1, 1, 0, 1. Now we have P1. So how will we find P1? We will have XOR operation between 3, 5, and 7. So that is 1, 0, 1. 1, 0, 1. Oh, no, it's 1, 1, 1. 3, 7. Yeah, it's 1, 1, 1. 1, 1, 1. And that thing is equal to 1. So P1 is 1. Then P2 is XOR of 3, 6, 7. And that thing is equal to 1, 0, 1. That is equal to 0. Then we have P4 equal to XOR of 5, 6, 7. Again, that is 1, 0, 1, and that thing is equal to 0. So my final code will be this thing 1, 0, 1, 0, 1, 0, 1. 1, 0, 1, 0, 1, 0, 1. That is option 3. 1, 0, 1, 0, 1, 0, 1. So clear? You got where you were making your mistakes? Okay, okay, no issues. So now let's move forward to question number 13. So SRAM memory cell offers, so as I already told, the speed of operation is very high. So high speed. Other than that, it's costly. It has a high, very low density, and the power consumption is also high. Then we have another question. A DRAM cell stores the binary information on the external capacitor connected to it, the parasitic capacitor of MOS transistor, the external inductor connected to it, or the resistor. So the answer to this is parasitic capacitor of the MOS transistor, option B. Then we have DRAM memory offers low density, low cost, high speed, high power consumption. So it offers low cost. Density is quite high, speed is average, not that much, and the power consumption is low as compared to SRAM. So which of the following is not a non-volatile memory? So CD-ROM, magnetic disk, SD card, SRAM. Anyone? Yeah, correct. So SRAM is not a non-volatile memory. So Again, a question on this Hamming code. So, which of the following is a even parity Hamming code for the binary word 11111? So, you guys do it, then I'll show the solution. Yeah, you can also have odd parity. So here it's even parity mentioned, and also in the questions that was not mentioned, we assumed even parity, but we can also have odd parity. For that, we will have XNOR operation. Yeah. So I think you should assume even parity because these were the here it is mentioned. This is also from the NPTEL lectures I have taken previous years. This questions and the questions that I showed earlier were also from NPTEL. There also they haven't mentioned, but here they mentioned. So I assume whenever it's not mentioned, assume even parity, at least for NPTEL assignments and questions. But it should be given. Mostly it should be given. So let me just show the solution. By now, I think you guys are well versed with these types of questions. So if this question were to be in a competitive exam and you wanted to save time, you could just simply say for P1, P2, number of ones are 5, 5. For P4, P8, number of ones are 4, 4. So P1, P2 will be 1, 1, and P4, P8 will be 0, 0, 0, 0. So in that way, you could have easily gotten the answer. So I don't know what I am doing. So sorry about that. So it's one. There is one. So P1 is XOR of 3, 5, 7, 9, 11. So this I was saying number of ones will be 5 because my code is 11111. So 3, 5, 7, 9, 11. Number of ones are 5, so it will simply be 1. P2 is XOR 3, 6, 7, 10, 11. Again 5, so 1. P4 is XOR 5, 6, 7, and 12 with 0. And P8 is 9, 10, 11, 12. That is 0. So my final code will be 1, 1, 0, 0. 1, 1, 1, 0, 1, 1, 1, 0, 1, 1, 1, 1. So option C, as you guys have uh, done it. Then I have question number 18. It states that a memory unit 1024 cross 64 is specified by the number of words and the number of bits per word. How many address lines are needed? So we have a memory unit. So memory unit is represented by 2 raised power k times n, where 2 raised to power k is your number of words and n is your number of bits per word. 2 raised power k is your number of words and k is simply your address lines. So as per the given question, we have 1024 cross 64 equal to 2 raised power k cross n. That implies 2 raised power k is equal to 1024. That implies k is equal to log 2 of 1024, that is equal to 10. 2 raised power 10 is equal to 1024. That was option C. Now question number 19. So again a Hamming code type question. I think we have done 4 or 5 questions based on this. So again I'd like you guys to do first, then I'll show the solution. This should not take much time. So it says that in a message transmission, suppose that the received Hamming coded message is 0111 1011 0110. Identify the location of the error in the received string. So find the error. So has anyone done it? I think by now you guys should be able to do it. No, I'm afraid that's the wrong answer. I think you have missed something. So let me just show. So you have 0, 0, 1, 1, 1, 0, 1, 1, 0, 1, 0, 0. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So C1 will be equal to XOR of 1, 3, 5, 7, 9, 11. So this is 0, 1, 1, 1, 0, 0, and that is equal to 1. Then I have C2 XOR of 2, 3, 2, 3, 3, 4, so 6, 7, 10, and 11. So that is 2, 0, 1, 6 is 0, 7 is 1, 10 is 1, and 11 is 0. So this is again equal to 1. Then I have C4 equal to XOR of 4, 5, 6, 7, 11. Sorry, 12. 4, 5, 6, and 12. So that is 1, 1, 0, 1, 0. That is again equal to 1. Then I have C8 equal to XOR of 8, 9, 10, 11, 12. So that thing is equal to 1, 0, 1, 0, 0. That is 0. So C8, 4, 2, 1 is 0, 1, 1, 1. So it's 4 plus 2 plus 1. That is 7th bit. So the error is at bit 7. Option C. Clear? So we have this question. Do it quickly. So we have this question. What is the length of the Hamming code for a given input data word of length 60 bits? So it should not take more than 30 seconds. So what will be the length of the data word of 60 Hamming code length of 60 data word of 60 bits? So we have seen this type of questions. So as I told you earlier, for Hamming code we have this condition 2 raised power k should be greater or equal to n plus k plus 1. Here n is 60, so 2 raised power k should be greater or equal to 60 plus k plus 1. So 2 raised power k should be greater or equal to 61 plus k. So let's just say k is equal to 6. 2 raised power 6 is 64, greater or equal to 61 plus 6 is 67. So incorrect. So n is equal, k is equal to 7. So 2 raised power 7, 128 is greater or equal to 68. Right. So k is equal to 7, n is equal to 60. So total n plus k is equal to 67. So option C is your correct answer. Now I have question number 21. So identify the functions f1, f2, f3 implemented by the following PLA circuit. So we have this PLA circuit and we need to find out f1, f2, f3. So let me just call the output of this AND gate 1 as A1. Similarly, A2, A3, A4. So AND 1 output A1 is equal to, so A1 is this term, that is C complement times B complement. So it's B complement C complement. A2 is A2 is this thing, B complement times B, so that is 0. Then we have A3. A3 is this thing, so this is C complement B A. A complement B C complement, right? Then I have A4. A4 is A B C. A4 is A B C. Now F1. F1 is A F1 is A1 A2 A4. A1 plus A2 plus A4. So that thing is equal to B complement C complement plus ABC. Yes. Then F2 is equal to A2 plus A4. So that is only A4 because A2 is 0. So this thing is equal to ABC. Then F3 is equal to A1 plus A3, A1 plus A3. So A1 plus A3, so A1 is equal to B complement C complement and A3 is equal to A complement B C complement. So F1 is ABC plus B complement C complement. F2 is ABC and F3 is B complement C complement plus A complement B complement C complement. So option B is the correct answer. Any doubts? So any doubts? Any doubts in this question or any other question? That was the last question of today's live session, but if there are any doubts in this question or any other question. Okay. So apart from the one of the participant that is quite evident from the name, you guys are doing your bachelor's or you are in some other courses. So you are, I assume you are bachelor students, right? Okay, that's nice. So that was all for today's live session. We'll meet next time, that is next Sunday from 3 to 5 p.m. Where we'll be discussing week 10 live week 10 related questions. It will be Sunday 3 to 5 p.m. hopefully. So thank you so much for joining. If there are any doubts, you can ask next time. Okay, thank you.